Testing network transports doesn't have to mean spinning up separate processes or managing complex infrastructure. We'll demonstrate how FastMCPs run server sync. Fixture lets you test real HTTP connections in process with automatic cleanup and full debugger support, all while keeping your tests fast and deterministic. This pattern gives you the realism of network testing without the usual headaches.
Import pytest. From FastMCP, import FastMCP client. From FastMCP client transports, import streamable HTTP transport. From FastMCP utilities tests, import run server async. Def create test server, FastMCP. Create a test server instance. Server equals FastMCP, test server. At server tool. Def greet name, SDR. Return hello, name. Return server. At pytest, fixture. Async def HTTP server, SDR. Start server in process for testing. Server equals create test server. Async with run server async server as URL. Yield URL. Async def test HTTP transport HTTP server, SDR. Test actual HTTP transport behavior. Async with client. Transport equals streamable HTTP transport, HTTP server. As client. Result equals await client ping. Assert result is true. Greeting equals await client, call tool, greet. Name, world. Assert greeting data equals hello, world.
This demonstrates the fixture pattern combined with in-process network testing, a powerful approach for testing network services without external dependencies. The test creates a complete server-client ecosystem within a single Python process, using pytest fixtures to manage lifecycle and dependencies. What makes this distinctive is its ability to validate real transport behavior while maintaining the speed and determinism of unit tests. The pattern works by running the server as an async task within the test process, exposing it through a local URL that the client connects to. This maintains complete isolation between tests while exercising the actual network stack, from serialization to transport protocols. The separation between fixture setup and test logic keeps tests focused on behavior rather than infrastructure, following the principle of self-contained verification. This approach solves the classic trade-off between realism and speed in network testing. You get production-like validation of your transport layer without the flakiness or slowness of external services. It's particularly valuable for testing RPC frameworks, API clients, or any system where transport behavior matters. The only trade-off is that it can't test true cross-process scenarios, which is why frameworks like FastMCP reserve sub-process testing for specialized cases. Let's break it down.
Import pytest. From FastMCP, import FastMCP client.
This imports pytest for test infrastructure and FastMCP with its client class, the core components for creating AI callable tools and connecting to servers. The client handles all transport logic, abstracting HTTP WebSocket details from your test code.
Def create test server, FastMCP. Create a test server instance. Server equals FastMCP, test server.
This factory function creates a minimal FastMCP server instance for testing. It isolates test cases from production configuration, ensuring consistent behavior across test runs. The server name, test server, identifies this instance in logs and error messages.
At server tool. Def greet name, SDR. Return hello, name.
This at server tool decorator exposes the greet function as an AI callable tool. FastMCP automatically generates the tool schema from the type hints and function signature, enabling type-safe AI integration. The pattern here is key. Decorating functions with @server tool transforms them into remotely executable endpoints while maintaining pure Python syntax. This is how FastMCP bridges Python logic with AI workflows.
Return server.
Returns the configured FastMCP server instance with the registered greet tool. This enables the test fixture to start a fully operational server for HTTP transport testing.
At pytest, fixture. Async def HTTP server, SDR. Start server in process for testing. Server equals create test server. Async with run server async server as URL. Yields URL.
This is pytest's fixture pattern for reusable test setup. It spins up a FastMCP server instance before each test, then automatically tears it down afterward, ensuring clean test isolation. The yield provides the server URL to tests while managing the server's lifecycle.
Async def test HTTP transport HTTP server, SDR. Test actual HTTP transport behavior. Async with client. Transport equals streamable HTTP transport, HTTP server. As client. Result equals await client ping. Assert result is true.
This tests the HTTP transport layer by establishing a real connection to the test server. The context manager ensures proper connection cleanup after the test, while ping verifies basic connectivity before making tool calls. This follows the standard pattern of testing infrastructure before business logic.
Greeting equals await client, call tool, greet, name, world. Assert greeting data equals hello, world.
This invokes the server's greet tool with the argument name, world, then verifies the response matches the expected output. It demonstrates end-to-end tool execution, client request, server processing, and response validation. The assertion pattern here ensures the transport layer correctly serializes arguments and deserializes responses, confirming the HTTP transport behaves as expected. FastMCP network testing pattern. The run server async utility launches FastMCP servers in process for testing, using any I/O task groups to manage lifecycle while maintaining full debugger support. In-process testing is 10x faster than sub-process isolation, but requires proper async fixture handling to avoid event loop conflicts. This approach becomes the default for all network transport tests, where sub-process isolation isn't mandatory.
The server that never starts is the one you test most thoroughly.